Then, for example, here, predict the polarity of xenon fluoride, xenon tetrafluoride, xenon trifluorochloride. Here we have dichloroxenon. So this is an example which is kind of similar to the one earlier, where we went from methane to carbon tetrachloride, CCl4, replacing one hydrogen with a chlorine at a time. So we're doing a similar thing here. We already saw xenon tetrafluoride, and it was polar. Or sorry, it was non-polar. I'm gonna say it was non-polar. But what happened whenever we had the this system? We went from non-polar to non-polar, but as we went along this path, we went through polar molecules. So maybe something similar will happen here. I don't know. You can do the same thing. You can continue it on and just change it with one more. So xenon fluoride, Cl3. But remember, we're not changing hydrogens this time. We're changing fluorines for chlorines. And then it could be the whole way this. Okay, so we've talked a bit about single bonds, double bonds, triple bonds, whenever we were considering Lewis theory. These different bond lengths are different numbers of bonds, like the single, double, and triple, can in fact have significant impacts on things like internuclear separation, so the distance between the two atoms involved in the bond. It can have effects on the energy of the bond. It can also just sort of influence some of its reactivity. And one of the ways in which we can rationalize this is through something called bond order. So the order of a bond is the number of bonding electron pairs shared by two atoms in a molecule. So typically bond orders may be 1, 2, and 3, as well as fractional values. So you can have half a bond sometimes. And bond strength increases with bond order. Bond length is inversely proportional to bond order. So as bond order increases, the bond gets shorter. So for example, if I have a carbon, is one of the most prototypical examples. So I have a single bond carbon. I then have a double bond carbon, slightly longer. And then this is a very extreme example, triple bond carbon. Oh, like this. So as the bond order, so it's bond order 1, 2, and 3. So as bond order increases, the bond length decreases. So bond order increase, bond length decrease. Okay. Then bond strength also increases with difference in electronegativity between the two covalently bonded atoms. Covalent bond strength increases with increasing delta chi. So example, HCl bond strength is stronger than HBr bond strength because delta chi here is larger than delta chi here. Covalent bond strength increases with increasing bond order. For example, O double bond O bond is stronger than O single bond. So the bond order triple, double, single, so that's the bond strength changes. Bond strength decreases with increasing bond order. This is the strength. So a double bond is shorter than a single bond. I already showed that with carbon. So here we have an example of a molecule which has single, double, and triple bonds. This is acrylonitrile. So we have here single bond between carbon and carbon. It's longer than the double bond between carbon and carbon, which is longer than the triple bond between carbon and nitrogen. And here we have hydrogen, hydrogen, hydrogen. Fractional bond order. So fractional bond order occurs in molecules with resonance structures. So here we have NO2 minus. It is a complex ion, shown here by its negative charge. It is an anion. Here we can have a resonance structure. So the double bond can be between this nitrogen and oxygen, or the double bond could be between this nitrogen and oxygen. And so we get some sort of average structure, which causes the bond order to be 1.5. So the bond order is the total number of electron pairs used for a type of bond divided by the total number of bonds of that type. So for example, 3 electron pairs in NO bonds divided by 2 nitrogen-oxygen bonds gives a bond order of 1.5. So here we have a double bond, which is 2 pairs of electrons, and a single bond, which is 1 pair of electrons. So it's 3 electron pairs, divided by the number of NO bonds, which is 2, which will give us 3 over 2, which is 1.5. Bond length then, so this is inversely proportional to the sort of the strength of the bond. Bond length is the distance between the nuclei of 2 bonded atoms. We discussed this before whenever we were looking at covalent radii. Here we have a schematic of energy versus internuclear distance. So there is some sweet spot here, some minimum where the energy is lowest at a certain distance. And so for the H2 molecule, we have a bond energy which is lowest at 74 picometers internuclear separation, so internuclear distance. So we have one nucleus there, we have another nucleus here. So the bond length is the distance between here and here. See here it varies for carbon, for chlorine, and then for carbon and chlorine, it is somewhere in between the two. Bond length then depends on the size of the bonded atoms. It also depends on somewhat the sort of electronegativity of the 2 atoms, and also a little bit on the bond order. So here HF is about 1.040 angstroms. So what an angstrom is written down here. It's 1 × 10⁻10 meters. Here, hydrogen chlorine bond is 1.31 angstroms. It's written as an A with a circle over the top. And then each I bond is 1.650 angstroms. Right. So the bond length depends on the size of bonded atoms. Here we have a few more examples in more complex systems. So a carbon-oxygen bond here is 1.410 angstroms. Then the bond length here depends on bond order. So we have a carbon dioxide. So this is a carbon-oxygen bond of 1.317 angstroms. So it's gotten shorter because it is a double bond. So bond length depends on bond order. As bond order increases, as we saw earlier, BO increases, then bond length BL decreases. Okay, and then carbon monoxide, then it has the shortest bond of 1.194 angstroms. This is because it is a triple bond. So bond distance is measured in angstrom, where 1 angstrom is 10⁻10 meters. So bond length and bond strength. Bond order is proportional to 2 important properties: bond strength and bond length. So here we have carbon hydrogen bond. It has its energy is 414 kilojoules. The energy of a carbon oxygen double bond is 745 kilojoules, even though the length is longer. The length is longer partially because these atoms are bigger than hydrogen, but also because the electronegativity difference. But ultimately, the thing that wins out here is the fact that this is a double bond. The bond strength and the bond length combine together to influence the bond order. Bond strength, bond enthalpy is the energy required to break a bond in a mole of gaseous substance. So in order to go from a Cl2 molecule to 2 chlorine atoms in the gas phase, we have to give it 242 kilojoules per molecule. So delta H is the enthalpy or the energy of that, and D is just meaning dissociation, so separation of the 2 chlorines. and we have Cl-Cl, which is equal to 242 kilojoules. Bond enthalpies are always positive because we always need to give information or give energy to break the bond. Energy is always required to break a bond. Delta H is always positive. Energy always released when a bond forms. Delta H is always negative for bond formation, and it's always positive to break a bond. Tabulated bond enthalpies are averages of a large number of molecules. Strengths of covalent bonds. The energy required to break a covalent bond is called the bond dissociation enthalpy, D. For the Cl2 molecule, D, Cl, is given by the delta H for the reaction. So the reaction is this one, where the chlorine molecule, Cl2, in the gas phase becomes 2 chlorine atoms, Cl gaseous. So when more than one bond is broken, so for example here, we might have many more or much more energy. So like, for example, methane here is CH4 in the gas phase. So in order to dissociate this, we dissociate it completely. So we get carbon and 4 hydrogens like this. So delta H for this total process of the total dissociation of methane, delta H is equal to 1,660 kilojoules. The bond enthalpy is then a fraction of delta H for the atomization reaction. So that's a quarter of this energy. So the dissociation of a single CH bond is going to be 1/4 delta H, which is equal to 1/4 times 1660 kilojoules is equal to 415 kilojoules per CH bond. The reason why it's 4 is because there are 4 CH bonds in methane. Remember, methane has a tetrahedral structure, something like this. H. And so there are 4 carbon-hydrogen bonds, which result in us having to divide our total atomization enthalpy by 4. Example of the formation of a covalent bond. So here we have hydrogen plus chlorine giving 2 HCl. So we'll need to calculate the delta HR for the reaction using tabulated data. So delta HR for this reaction is going to be equal to the sum of the delta H for the H2 bond breaking. So it's going to be the sum of the delta H of bonds breaked minus the, so it's broken bonds, minus the sum of all of the delta H's of the formed bonds. So in this case, we're going to be breaking one H, so H2 is HH, so we're going to be breaking an HH bond, and then Cl2 is Cl-Cl, so we're going to be breaking a Cl-Cl bond, and then we're going to be forming 2 HCl bonds. So the energies for this are given on this side. So the average bond dissociation enthalpies are written here. For hydrogen, it's 436 kilojoules per mole. For chlorine, it's going to be chlorine-chlorine bonds are going to be 242. So it's going to be the sum of, what did I say, 436 for the hydrogen-hydrogen bond, plus 242 for the chlorine-chlorine. Minus the bonds formed, which are going to be HCl bonds, but there are 2 of those, so it's going to be 2 times whatever that value is. So 2 times HCl, 432. We then put that into our calculator and we get a value for delta HR. So it's 436 plus 242 minus 2 times 432 is equal to minus 186 kilojoules per mole. So this is a negative value, which means it's exothermic, which means that this is a process which is likely to proceed. We'll discuss more about that in Gen Chem 2, but for now, because of the negative charge, we assume that this is going to proceed. Then we want to know what the energy, the E-min for a Cl-Cl bond is, and what an HH bond is. So we'll just do it for Cl-Cl, and then I'll let you do the HH bond yourself, just to sort of like make sure that you're familiar with the process. So these are going to be the minimum energy required to break a Cl-Cl bond. We want to know what the energy for a mole of Cl-Cl bonds are, so that we can find out what 1 mole or what 1 bond energy will be. So we know that delta H for the dissociation of Cl-Cl bond is going to be plus 242 kilojoules per mole. So then we need to divide by Avogadro's number, so that's kilojoules per mole, all over Avogadro's number, which is 6.022 times 10 to the 23 for 1 mole. And so that's going to be equal to, put it into our calculators. We'll have 242. So convert this also into, so times 10 to the 3, this, so that it's in joules. And then, so it's 242, 242 times 10 to the 3. Divide that by 6.022 times 10 to the 23 gives us a value of 4.02 times 10 to the minus 19 joules. Okay. And that's the energy, or sorry, that's going to be E-min for the chlorine bond. Shouldn't be delta H. It should be E-min. So then just do this then for the hydrogen bond. It's pretty much the same process. And then you can proceed further. Here is the table of all those bond enthalpies. You can see that they change based on sort of like the size, the length of the bond, the strength. Like there are various reasons for the changes in the energies. For example, you can see that a carbon-hydrogen bond is weaker than an oxygen-hydrogen bond, but nitrogen-hydrogen bonds are even weaker than that. And you can just sort of see the different trends that exist. Some bonds don't form, like silicon-nitrogen bonds or nitrogen-phosphorus bonds, etc. Those just don't form. They're not known to form anyway. And so then bond strength then is given here, where we have, we can just have a look at the different bonds. So we have hydrogen-hydrogen bonds. They're 436 kilojoules per mole, quite hard to dissociate. Carbon-carbon bonds then somewhat weaker. But then carbon-carbon double bonds much stronger, carbon-carbon triple bonds really strong, and then nitrogen-nitrogen triple bonds incredibly strong, 945 kilojoules per mole. And this is one of the reasons why N2, nitrogen in the air, is not really reactive at all, because this bond then it requires a lot of energy to separate the nitrogens from each other. So the greater the number of bonds, the bond order, the higher the bond strength, and the shorter the bond. So these bonds are getting shorter as we're increasing the bond order. And so that brings us to the end of this chapter. So let's move on to the next chapter. Okay, so chapter 9, bonding and molecular structure, orbital hybridization and molecular orbitals. So this is basically how we take what we've learned about valence occupancies, electron configurations, and Lewis structures, geometries and start to understand how exactly electrons can be shared. Like, we've talked about how a covalent bond is sharing of electrons, but we also know that electrons only exist in certain regions of space. So what if how do those electrons come into contact with each other? How do those regions of space, the pi orbital has or the p orbital has a shape like this, or the s orbital has a shape like this. How do those interact with each other, and so on, and how are they then able to share those electrons? And so that's where we're going to be looking at some of these models. Orbital hybridization is one model. Molecular orbitals is another model, which won't really be covered in a huge amount of detail here. We'll talk about it, but orbital hybridization is kind of the simpler model that works well for the main group elements that we'll be considering. So yeah, so there's the three parts. There's orbitals and theories of chemical bonding. There's valence bond theory, which will make up the bulk of what we'll talk about, and then there's molecular orbital theory. So if we remember way back to chapter 6, it told us about the location of the valence electrons in an atom and how that's described by the orbital model. So we learned about the Bohr model of the atom. We learned about orbital filling. The order that we filled them in was based on the quantum numbers, n plus L. And then it should seem reasonable that an orbital model can also be used to describe electrons in molecules. Because if electrons exist in orbitals and electrons are shared, those orbitals have to, meet each other or interact with each other or overlap. Otherwise, how can they bond? In this chapter, you will explore two common approaches to rationalizing chemical bonding based on orbitals. One is valence bond theory. So that's the one that we'll spend most of our time talking about. And the other is molecular orbital theory, which is a more detailed theory, but it's not really something that we're going to go into too much detail here. Valence bond theory. So bonds are formed when orbitals on atoms overlap. So that's the kind of if we're going to share electrons, they have to meet each other. They have to be able to come into contact with each other. We have to form, especially for the sigma bonds that we've talked about, they have to form, say we've got a carbon-carbon bond, they have to meet somewhere in between the two carbon atoms. There has to be somewhere in this region here, there has to be some overlap between their orbitals, otherwise they won't be able to share those electrons. And so orbitals have directionality. The p orbitals, 1 point's up, 1 point's left, and 1 point's in and out of the page, the px, py, pz. And so the bonds can kind of be viewed as a bit of a chemical handshake, I suppose, where the two atoms, I guess, reach out with their orbitals or reach out with their hands and then, sort of shake hands. And that's the sharing of electrons. One electron from both atoms form a bond. That's our covalent bond. So valence bond theory was a way of rationalizing how these orbitals can be shared and how the electrons from those orbitals can be shared. So the premise here is that bonding involves the valence electrons, and that's something that comes over from Lewis theory as well. Whenever we don't really consider the core electrons, we're only considering the valence electrons. And we have half-filled atomic orbitals on bonding atoms which overlap to form bonds. Bonds are then localized between the atoms or as lone pairs, and this leads to the prediction of molecular shape. So what does this sort of mean? Well, it means the bonds are localized between atoms. So this is this idea of, the carbon bond or the carbon hydrogen bond or whatever covalent bond it happens to be. The electrons have to meet each other. I mean, if the orbitals don't at least overlap a little bit, then there can be no bond. They have to handshake. The handshake doesn't exist if the two hands are separated. But the bonds are localized between the atoms. They're along this bonding axis. This is like a sigma bond that we learned about before. So the way that these orbitals are localized leads to the prediction of the molecular shape, sort of like our tetrahedral shapes, our trigonal bipyramidal, our octahedral, and so on. And the half-filled is because, well, every orbital can only contain 2 electrons, and those orbitals must overlap and be shared, or those electrons must be shared to form a covalent bond. And so if we have a fully filled atomic orbital, then it cannot be used in bonding in a normal covalent bond. Here we have the orbital overlap in the H2 molecule. So this is a very simple molecule where there's only 1 electron from both atoms. So it forms this HH bond, the H bond like this, and that is a sigma bond. So what happens is if we look at, okay, so this is this totally separated case where we've got a hydrogen atom and a hydrogen atom. We can see that they are spherical. That's because the electrons exist in our s orbitals. You know, hydrogen is 1s1. It only has 1 electron, and that electron is in an s orbital. S orbitals are spherical, if we remember back to, I think, chapter 6. That was in module 3. So there is no overlap, no attraction when widely separated. So whenever there are 2 atoms that are far apart, there's no overlap between the orbitals. There's no sharing of electrons. There's no bond formed. But as we bring them closer together, we start to see that there is bonding and that they do share those electrons. And so this red color here indicates that there is a high density of electrons, or a high probability of electrons existing in this region. And that makes sense because that region is immediately between the 2 nuclei, which are these black circles. And those black circles represent the hydrogen nuclei. They form a sigma bond whenever they share their covalent electrons. And so those electrons should be localized along the bonding axis if it's going to be a sigma bond. And then obviously this red area gets larger as the nuclei come closer together. The bonding potential energy decreases as the bond strength increases. And so we reach some minimum here in energy, which is the maximum point of hydrogen-hydrogen attraction. It has some distance between the nuclei. In this case, it's 74 picometers, so it's very small. And it has some bond energy of minus 436 kilojoules per mole, which means that it is a reasonably strong bond. Then after we do this, will you say, like, well, what happens if we keep doing that? Well, ultimately what happens is nuclear repulsion starts to play an effect. So the nuclei are both very positive centers. They kind of repel each other. And so as we bring them closer and closer together, the energy rapidly increases as those nuclei want to repel each other. So there is always some sort of trade-off between the attractive nature or the positive effect of bonding on the energy and the repulsion between the nuclei. So again, a sigma bond is defined as a bond in which electron density lies along the axis of the bond. So why do covalent bonds form? So potential energy is minimized for 2 hydrogen atoms when the nuclei are 0.74 angstroms apart. So that's angstrom. It's got a little circle above it. It's a Swedish letter, I think. So angstroms are typically used to describe bond lengths. So the energy, for example, the energy of the H2 molecule is minus 436 kilojoules per mole, below that of 2 separated hydrogen atoms, which means that that much energy is released whenever you form a bond, and the release of that energy obviously stabilizes the system. So you'll learn more about thermodynamics in Gen Chem 2. Types of bonds. So sigma bond is the overlap along the nuclear internuclear axis. So that's the connecting line between the 2 nuclei. So typically, if we recall from our Lewis structures, we draw a line like this to indicate bonding. This is in fact a sigma bond, given the Greek letter sigma. This is whenever the electron density is sort of positioned between the 2 nuclei, and that's what we saw with, you know, the red region in the H2 model, or energy versus potential energy versus distance graph. A pi bond then is something different. So this is the overlap above and below the internuclear axis. So whilst a sigma bond is going to be along our internuclear axis, there are orbitals which are orthogonal or at 90 degrees to that to this bond, and so those can be in the case of carbon, they can be the p orbitals, like so. And so these p orbitals are orthogonal, but they can still hold electrons. And those are the electrons that are in there, if they're half filled, can also be shared. And so it can be that we can share the electron density above and below the sigma bonds. And so this is called a pi bond. And indeed, there is another orbital which is at 90 degrees to that, which is another p orbital. It comes in and out of the page like so, kind of like this. I don't know if that really can be, if you can see that, but like basically there's a p orbital which goes up and down, and then there's p orbital which comes towards us and goes away from us. And so that can also, the electron density can also be shared there. And that's the origin of our double and triple bonds. But we'll see a lot more about that as we go through. So that's not entirely clear yet. So the example that we saw was for the simple H2 atom, where we have the overlap of two s orbitals. So two s orbitals overlap. Here we have the hydrogen 1s orbital, and here we have another hydrogen 1s orbital, both from separated atoms. And then if we bring them together, we notice that as we bring them closer and closer together, we see a decrease in energy and then an increase in energy as they get too close together. So what happens is that they're forming this bond, they're sharing those electrons. And the sharing of those electrons creates this hydrogen-hydrogen sigma bond. So then this is not the only way. It's not just two s orbitals can overlap. We can actually overlap different types of orbitals. And so that's what happens in the case of fluorine, or what can happen in the case of fluorine. So we can overlap a hydrogen atom with a fluorine atom. And so the 1s orbital of hydrogen could overlap with the 2p orbital of fluorine. So this is a p orbital. I typically draw it like something like this, but the real picture is something more like what is on the screen in front of you, this much larger sort of half moon or half sort of circle type shape. So you might also notice that the colors here, so this is kind of like a purplish color, and this is also like a purplish color. So the hydrogen 1s orbital and this part of the 2p orbital have the same color. It means that they're in the same phase, and that means that they're capable of overlapping in a bonding manner. So they have the same symmetry. They're both pointing along the same axis. They're pointing towards each other. And so they can overlap and form a bond like this. So here we have an overlap of an s and p orbital. Now these are the very sort of quite straightforward examples, because it's this internuclear axis happens to lie exactly along the HF bonding axis. There's no real ambiguity here. But eventually, like, you might be thinking, well, some of the molecules that I've encountered, like methane and water and things like that, they don't really have nice linear bonds. They're not just really linear complexes like HF, or in the case of F2 down here. And they don't, how do we then form these sigma bonds? Because I mean, water has its oxygen hydrogen bonds. We can't really refute that. Methane has its carbon hydrogen bonds, but how does that happen? And so if this is the way that orbitals are arranged. And so one of the ways that we rationalize that is using valence bond theory, and how we'll figure that out shortly. And then the bottom here, of course, if we can have a p and s orbital overlap, and if we can have s and s overlap, then why can't we have p and p overlap? And so that's what happens in the case of fluorine. So the 2p orbital of fluorine and the 2p orbital of fluorine overlap to form a sigma bond. You'll also see here this kind of grayish blue color of the orbital overlaps, and we form this sigma bond where the electron density is going to be localized in between the two nuclei. And so, yeah, so long as they're like a similar color. So usually if you're just doing it with one color, you might draw it like this, and then you might color in one half, like the top half, for example. And then those would need to be like, you'd need to match up the colored part. So this is maybe the fluorine-fluorine bond, for example. So the colored parts would overlap, and then you could form a bond like this one. So valence bond theory, this is how we really create a system wherein the bonds, like for example in methane or water, can be rationalized. So the main points of the valence bond approach to bonding are that the orbitals overlap to form a bond between two atoms. So this is like what we just saw, like the handshake idea. Lewis theory tells us that electrons can be shared in order to form bonds. But how does that work under certain geometries? We also know that from VSEPR that orbitals, bonds and lone pairs repel each other. And so that means that we have these geometries which are not on a perfect sort of XYZ axis. So how do they overlap is a key question. And valence bond theory attempts to explain this. Overlapping orbitals hold two electrons of opposite spin. Remember, we have the MS quantum number and the idea from the Pauli exclusion principle that no two electrons can have the same set of quantum numbers, or exactly the same set of quantum numbers. And so usually one electron is supplied by each of the two bonded atoms. The bonding electrons are localized with a higher probability of being found within a region of space between the bonding nuclei. Both electrons are simultaneously associated with both nuclei. So this is the idea that even though the electrons are shared, both of them have access to them in a covalent bond. Although, of course, if we recall from our electronegativity that maybe the electrons are closer to one nuclei than the other, but ultimately both have access to them so they can fill their octets or they can fill their duets. So this is, so sigma bonding is whenever the bonding electrons are localized with a higher probability of being found within a region of space between the bonding nuclei. So for example, carbon, so it's between the nuclei that are being bonded. And so this is the bond, and then this is a sigma bond. The electrons in this bond, this is a homonuclear diatomic bond. So it means that the electronegativities are the same, which means that the electrons will not be pulled in one direction more than the other. So here are some of the terms that we might see. Some of these might not make sense just yet, but don't worry, they will do. These are sort of the terms that we'll need to be familiar with. Some we will already be familiar with whenever we read. Some will become more familiar as we go through. So valence bond terminology. So overlap, so two orbitals existing in the same region of space. So remember that orbitals have some shape associated with them. Like a p orbital is like that, an s orbital is like this. And so an overlap is whenever they touch each other or they handshake. A lone pair, LP, so we've come across that in Lewis theory. So this is a non-bonding pair of electrons. So they're both paired, both on one nuclei. They're not really involved in bonding to any great extent, at least covalent bonding. Bonding pair electrons, so BP, that's the result of orbital overlap. This is whenever we share one electron from each molecule, or each nuclei, sorry. Central atom, so this is the atom of concern in a molecule. So if we recall back to our molecular geometries on our electron domain geometries, this like AX notation, where A is our central atom and X has some value N. The hybridization then is the linear combination of atomic orbitals. This is obviously one of the things that we're not quite familiar with yet, but it's this idea that atomic orbitals can be combined in order to make orbitals which point along the bond axes. But we'll talk about that shortly. Hybrid orbital is then the result of this hybridization. So these are the bonding orbitals that arise from the mixing of the atomic orbitals. A sigma bond is the overlap of orbitals along the bond axis. So that's, you know, this idea of hydrogen. So that's a sigma bond between those. A pi bond then is overlap of orbitals above and below the bond axis. So that's, well, it doesn't work in hydrogen, but it can work for carbon. So it's like if we have a carbon bond, it's a sigma bond that I've drawn right now. So if I have then like a p orbital here and here, those, assuming that they have the same phase, so I'll color in the bottom part so it works. The electron density can be shared between these, and that forms another bond. That's a pi bond. So basically, because of the sideways overlap, I guess, is what a pi bond is. So it's the overlap of orbitals above and below the bond axis. Then, so sigma bond is a single bond is one sigma bond, a double bond is one sigma bond and one pi bond, like this. This is a double bond. And then if we have a triple bond, what we have is one sigma bond and two pi bonds. So that can be a case where we have, change my pen color to something cyan, why not? Whenever we have the other p orbital, which can point like in and out of the page, so our axes are like this: Z, X, Y. So that would be our, these would be our px orbitals here. They can overlap on the sort of sideways, in and out of the page. And so that's a triple bond. This is also a pi bond here, this one in this blue or cyan color. So we've got two pi bonds and a sigma bond in the middle part here. And so that would be a triple bond. But we will talk a lot more about this as we go through. But these are just sort of the terms that you'll hopefully be familiar with by the end of this section. But there's like, what, 20% of them or 30% of them we already know. So we're not starting from nowhere. A sigma bond, it looks like this. When bonding occurs along a bond axis, it is referred to as a sigma bond, given the Greek letter sigma, which is this one, that's sigma. So we have a nuclei X, a nuclei Y, and or nucleus X and a nucleus Y. They are bonded together covalently with a sigma bond. The electron density is represented by this blue oval. Two electrons are inside of that blue oval, so this is the overlap between them. They're shared, and this is a sigma bond. So the electrons occupy the space between the nuclei predominantly. So that's the, if we remember back to the hydrogen case that we looked at earlier, that's the red area in that figure. Pi bonding then is bonding above and below the bond axis. It's referred to as a pi bond. So this is the overlap above and below the X and the Y. So remember, we still have the sigma bond here. We can't have a pi bond really without a sigma bond, not normally. And so that's the sigma bond is along the internuclear axis. The pi bond then is above and below any sigma bonds. And so then if we combine them together, this would be a double bond here, because we have a sigma bond plus a pi bond is equal to a double bond. So a double bond is made up of a sigma and a pi bond. So you can see here, there's a sigma here in between the nuclei and the pi bond, which is above and below the sigma bond, or above and below the internuclear axis, I guess is a better descriptor. Hybridization of orbitals, so explains both the formation of electron pair bonds and the observed geometries of the molecules. So we have to, you know, with water or with methane or whatever, methane we'll get onto just in the next slide. We have methane structure like this. And then it's got the hydrogen here, 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 and here. So it's got 4 hydrogens. If we look at our XYZ axis, so that's going to be our X, our Y, and our Z. So these are like coordinates from like maths or anything, geometry or whatever. If we like think about carbon, it's what its valence is. So its total electron configuration is 1s2, 2s2, 2p2. So that means, like, first of all, it has 4 valence electrons. So that means it can 4 VE, 4 valence electrons, means it can form up to 4 bonds from Lewis theory. But if we think about like where its orbitals actually are, so it's p orbital, 1, 2, so that's its pz. I'll just put z. So that one kind of lies along this bond here, this carbon hydrogen bond. So we could, in theory, describe that using our normal understanding. So like kind of like the fluorine hydrogen system. Then if we look at the p or the py orbital, so that's our y orbital, doesn't really overlap with any of the bonds. And then the same thing happens with the X as well, because remember this H atom kind of goes down and towards us rather than straight towards us. So it also doesn't really like overlap with any of the bonds, but yet the bonds still form. Isn't it amazing? So one of the things we have to try and do is try to account for that. And so that's where our valence bond theory